ฮัลโหลครับไม่มีเสียงในซูมครับผม
ไม่ใช่มั้งมิมใช้ไมค์ของตัวเนี้ยค่ะ
โอเค we can hear you now เสียงเราแล้วครับ
Okay. So that need. Okay, thank you. So maybe I start it again. Today I'm going to talk about how we use ultra-cold atoms for quantum simulation. So mainly I would talk about my experience that I gained from working abroad. And also, of course, I'm going to talk about quantum simulation. Let me introduce you first what are cold atoms and how cold it is. So if we talk about the temperature of room temperature, it would be about 300 Kelvin, which is sound high, right? What we are talking about in cold atom is over here in the micro Kelvin regime. So it actually like 6 order of magnitude colder for the first stage of cooling. But if we keep further cool them down, we could reach the upper limit at the bottom here, which is the quantum degeneracy state. That actually like a billion colder than the room temperature, the billion times colder. So it's extremely cold, and it is nowhere else in the universe that can cold as what we can do in nature. So this is actually much colder than nature could provide. So how do we do that? It's very technical detail, but let me show you a bit of the idea. Okay, so if of course we are physicists, so we know about Maxwell-Boltzmann distribution. So actually temperature and velocity are connected somehow. If you already know about Maxwell-Boltzmann distribution, for the green line, which is the at the temperature 2, if the temperature 2 is hotter than T1, which is the red line, then you can see that in average the velocity would be higher. So somehow if you go colder, that means you actually want to slow down something, which is atoms in this case. So what we want to do is slow the atoms down. That's how we cool atoms. Why do we want to cool atoms? That sounds weird, right? Actually, when we want to measure something, it have uncertainty that come from the temperature broadening. And if we want to measure something in very, very precise, what we want to do is we want to cool them down. In the first idea, they want to have a very precise atomic clock, which is a very useful tool for many things. What I can come up with like GPS and more things. Of course, everything about time that we use nowadays. When you want to do some network or something that you want to sync time, you also need the clock, right? So have a very precise clock was the initial idea to start doing cooling. And of course, if you want to cool them down, we want to slow the atoms because of the motional effect. And the techniques, the typical techniques that we use are using laser cooling, and then we trap it with the electromagnetic trap. Usually it is a magnetic trap. How do we cool atom with laser? That's quite interesting. Sorry. So what we do is we shine the light into the atom. So you can see from the big red arrow here, the light actually consists of many photons, and it shines into the right direction on the screen. Atoms will see the light, and then it absorbs and emits. However, the light that it absorbs is actually come from one direction, but the emission is actually random. So it can emit photon in any direction. So in total, when it absorbs and emits photon many times, it actually get the momentum kick from the photon that it absorbs, because it's always absorbed in one direction, but the emission is actually averaged to be 0 for the momentum. So it always absorbs from one direction, right? In this case, now we know how to imprint the momentum into atoms by using photons. The thing is, how do we slow it down? That means there needs to be some trick to make the atoms that prefer to absorb photon in the opposite direction of their movements, right? So it's try to absorb only the photon that's come into the head-on direction instead. So that is very easy answer. So you could use Doppler effect for that, to bias, to actually have a bias between the one that head on and the one that move into direction, into the same direction, to have a different absorption rate. So we use Doppler effect in this case. So from the Doppler effect and the absorb and emission photon, we can actually have a trick to cool atoms, to slow down the atoms. But we not just want to slow them down, we want to trap them as well. So what we do is we actually apply some magnetic field, not some, but it need to be quadrupole field that have 0 field at the center, that and then the atom would try to seek to the 0 field position such that they are accumulated at the center of the field. So to conclude this, the photon actually slow atoms down. The magnetic field tell the atoms where to accumulate. So at the end, we can trap atom in some position, as I show you on the right picture. That is a cloud of atoms that actually have temperature lower than room temperature for six order of magnitude. So it's very cold. This picture was recently take a picture at our lab, QSIM lab, last month. So it's very new, this result. It actually, yeah, it's hard to see. It's here. Yeah, it's just small dot. So it's like a millimeter size. So it's very small. We didn't measure that yet, but usually it's in the order of millions. So it's quite a lot. Yeah. So actually, it's funny that the group, actually, it's not only me that do this experiment. It's me and Ajahn Paul Narupon as well, and also our students that actually help us to do many things to get this work done. It's actually remind me the first mod in Thailand that we have done also with the same persons, which is me and Ajahn Paul Narupon. So we did it 11 years ago. It's a really long time, but after 11 years ago, we do the same thing again. That's very fun. Very funny, but it's also a bit sad. But okay. What's the difference in time? What? It's more stable. Is that what you say? I would say so I would say in the beginning when we did mod in 2017, we did it at the time. I was a PhD student here in the University of in Chiang Mai University. So it actually I just know that I need to do mod for doing something in quantum stuff. I have no clue why I need to do it, but I just do it because my advisor says so. Such a bad student, right? But it's very challenging. It's very hard. I need to do everything by myself. All the circuit and things, stuff, small thing need to be done, and then like lasers, I need to do it by myself. At the time, I never know before what mod is, how it would look like, and what I need to do. It's take me very long time to finish it. I would say without Ajahn Thaw present here in 2011, it might take me more than a year to finish it. But Ajahn Thaw was really helpful at the time. Also helpful now, but okay, yeah. What is the size of this cloud? Is there any electric and magnetic field around this cloud? Yeah, the size of the cloud is about a few millimeters. And yes, there are magnetic field to confine the atoms. Electric field, yes, but it's very low effect here. So we don't consider that. Yeah. And okay, come back to the mod today. So so anyway, even though we do the same thing, but the difference would to answer your question, the difference would be the experience that we have, because we have done it before. We know exactly what we are looking for and what we do it for. So what the aim of doing this time is we want to create to trap single atoms array, and we're gonna use it for quantum simulation, and that's the aim. We have a solid plan, and we know exactly what we need to do because now we have much more experience. Yeah, I know it now. It was a bit funny, but it's a bit sad as well. That at the time I I was in the shadow. I'm not so sure that what I'm doing and what I'm looking for. So it's exactly. Exactly. Okay, so yeah, much faster. Um, I I I think I should mention this. When we did it on 2011, the first mod in Thailand has been cleared at 2 a.m. So we actually work very hard at the time to make it done. It's not easy to get it at all. But for this one, we get it on the afternoon. Some days we say, okay, let's try it again. So it's much different. Yeah, it's there. Yeah. Thank you. Okay, so just go back to 2011. I was what?
I have a question about the role of the magnet. Is it just to cancel Earth magnet or
Uh,
anything
I
to trap?
see. So you asked me if the magnetic field that we create is actually for cancel the Earth field. Is that the question? Not really. It's like we want to do a magnetic field gradient. So it's very high gradient. It's about like 10 Gauss per centimeters. So at the center is 0, and then a center away, a centimeter away, it would be 10 Gauss around it. And further is even higher. So atoms would notice the energy shift due to the magnetic field, and it actually have force on the atom. This is actually the force combined with the light, and so it's actually forced to go to the field 0 at the center. That how the magnetic field work. So we use anti-Helmholtz coil to generate magnetic field. So it's generate quadrupole coil in this case. Okay, we have one more question about this is charged cloud or not. No, it's neutral atoms. So I should mention that as well. So we use rubidium 85. Rubidium 85. It's from Zeeman effect. So they're gonna have energy shift depend on submagnetic states of atoms. Okay, yeah. Any questions? Okay, so I can continue. So I just still at my experience at PhD. Let me continue. What's next? So when I was PhD, I have a good chance to went to University of Otago. It look like this. It's very beautiful places. It's a lot of good memory there. So I have a chance to go there and do a short experiment there for a year during my PhD. So I have a chance to do experiment about single atom trap and also ultra cold atom, ultra cold. Oh no, it's not ultra cold. It's cold atoms collision. So it's very good experience there. So and that actually also helped me to finish my PhD as well. So after I finished my PhD, I just tell my my co-supervisor, which is what in the University of Otago, that okay, I got my PhD. It's very helpful that I used to be there. So he actually just give me a position there as a postdoc. He offered me a position. So it's made me know that, okay, when I was there, I did a very good job such that he offered me a position immediately after I got my PhD. So it actually give me a bit more confidence, because of when I was young, I was really shy and not confident about myself, my experience, blah blah blah. But I just feel more confident at the time. And then I go back to the University of Otago for the second time as a postdoc. At that time, it's very different from the first time that I went there, because of instead of being a student, now I am treated like a worker, a colleague, that I work there. I really work there as a postdoc. And you feel a lot of not respect, but responsibility, and also pressure. It comes with pressure. So but it's a very good time there. So I actually built up my experience on single atom experiment there. I would like to show you some pictures that look very nice here. The pictures from Otago, that there are mud cloud. Here you might see more how to say that, the reference of size, how small it is compared to the this one is is just a lens, a powerful lens. So you have a powerful lens next to the cold atom cloud, just to zoom in how it look like when it's left only one atoms there. So when I say powerful, it's actually have a name on it. It's high NA lens numerical aperture, which is mean you have a big diameter of lens compared to the focus of the lens, such that you have a big solid angle to measure something. And that for measure the fluorescence of single atoms. So with this powerful lens, of course, it's not only a lens, it actually need to be an imaging system that powerful as well. So you can see individual atom as see here. There are two atoms in the pictures. So one on the left and one on the right. So we actually keep it there with an optical tweezers. So you shine a strong light to create a potential and trap them there. So then we can even move individual trap by just move one of them close to each other. And at the end, you load them into the same trap and let them collide. That's how we did the experiment in the past. And then you have exactly two atoms and then see the collision between them. At the time, it's what really excites me. It's like if you see the collision of the cloud, you actually measure only the average measurement of the cloud. But actually, some important point of physics is hidden under those ensemble average. You can see individual events, what actually happened. It's collide and release energy and so on. So you actually can observe individual of collision events. That is very make me very excited about it. So you see what people cannot see. At the time, the University of Otago is the one that have the best single atom preparation of the world at the time. Now actually it's changed, but yeah. But at the time I used to be a part of that, and very proud of it. I have spent my time there as a postdoc and built up my interest of microscopic study. So at the time, I still have some of unconfidence about my physics and knowledge and so on. But I feel like, okay, I know more things. I'm going to go back to Thailand and do something interesting. But actually, my supervisor there just told me that, Mim, you are quite good. You are as good as the other postdoc in the big group in the world, the best group. You can be there if you want. So he actually gave me the confidence to try to go to even a better lab. So even the University of Otago is quite good lab, but it's actually quite isolated as well. It is have limitation of funding as well. Not as much as Thailand, but it have limitation of funding as well. So but he said that I should try something very try to go to a lab of Nobel winner. That made me feel like, oh, can I try that? It sound like very, very interesting, and if I can be a part of them, it would be very, very good for me. So then I take a chance to try it. I think if he believe in me, I should believe in myself and try it. So I have applied for David Weiland group. He get a Nobel Prize in ion trap, in his ion trap. So he did he worked in what's the name of that? Not Chilla. It's the like a standard. He worked at NIST. So it is a competitive place to go. A lot of good candidates would like to go there because it's a good future there. You can imagine, right? I have been there. I was invited to be a invited speaker there as a candidate. I went there and give talk. They interest in me, I interest in them, but somehow I don't feel like I really like to work there because of some reason. Of course, I also try another one with Immanuel Bloch group, which is at the time is I would consider as one of the best group to do quantum simulation and have a microscope study. So you can see individual atoms and see how they work together and try and do the simulation for some interesting Hamiltonian. And then I applied there. I was invited to be there to give a talk. So it actually a nice experience to be a candidate there as well, because they actually pay you for the flight. They pay you for the hotels. They pay you for coming and give talk for them to listen. And okay, it's free. Why not? So I went there and give a talk, and they seem to be happy. And I actually like their labs very much. So I think this is the place that I want to work with. And so I joined that group. And that's how I went to Max Planck Institute of Quantum Optics. I would say it's one of the places that have almost unlimited funding. So if you remember, I need to make a laser by myself to do something. I need to do something. So we lacking of limit of funding to buy a laser that we want to use. But in that place, you have to use like 10 lasers and you have 5 more for spare. Like what they have in mind is not because of they're rich and they want to have a spare, but they think the most expensive is time. And they say whatever is broken, it needs to be changed immediately. And then we can continue without stop. Because buy a laser could take half a year and they don't want to stop. That's made me impressed, of course. And I have a lot of experience, good experience there. You would meet like Nobel winner walking around this building, and then you can talk to him if you want. So it's like in there, it's not a university, it's a institute for research. So there are a lot of genius people that actually have worked in like a leading of the world. So that's the best place to work for research, I would say. That from at least for me, that's what I feel. So like if I have a problem in the experiment and I stuck on some theory, Immanuel would just tell me, go to talk to this one, and the guy is just in the building. I don't need to go to anywhere, so we can just discuss about the problem. That's very nice. That's very nice. So I would hope that everyone here could have experience like what I had before. So just encourage you to do something that you maybe think that you are not good enough, but actually you are good enough, but you never think in that way. And you just need to try, like what I have done before, that I don't believe that I'm good enough to be there, but actually I am. And I believe that I do a good job there as well, as I noticed from people. So this is the experiment there. I can show you the pictures, how clouded it is. Not atoms, but cloud with optics and cables. You can see there are many lasers there. Each of them more than $1 million baht in Thai, but yeah, it's very expensive. We try to get more, but I mean in here in Thailand, but we need to take some time. But yeah, and also there would be a vacuum chamber inside there, but because of all of the optics, you can't see it. Lot of cables for computer control and timing control. So it's very complicated experiment. I would say somehow this place, you cannot work alone. You need more than one people for work inside the lab. Not because of it's dangerous, you can be shot by 600 amps of power supply that you use, but it's because of you cannot control everything by yourself alone. It's too complicated. You need at least 1 or 2 people to be around, and you need more people to think about the problem that we are facing on, because you cannot just read it on the literature review. It's actually in the frontier of physics where no one can give you an answer. You need to search for yourself. So it's very hard there. Working there is like very challenging. And that also a part of force us to work as a team. So you cannot work alone. You need to work in team. Otherwise, you cannot make it work. So this is a big team that I work with. Our team have like one master student, 4 PhD, 2 postdoc, and 2 PI. So that's a big team, right? So that's how we can actually do frontier physics. So you can see from the here in this picture is just a lot of monitors that we keep monitoring everything. And someone working on the laser on the left side. So actually we don't turn off the light like this, but it just make the pictures look cooler. So we just turn off the light and it's look good. Yeah. And that's one of the laser that we actually built by ourselves. So we want to use green color, a powerful one, but we don't, there is no nowhere in the market that sell green laser with this powerful. We need like 10 watts. So what we need to do is we need to do a laser by ourselves from 1064 lasers. So we do that doubling frequency stuff that it's jargon, so I don't need to. And that's me. I show this every time. I think people remember it. Okay, let's talk a bit about my recent work that has been published in Nature. So the theory about it is quite complicated. I have tried to give the talk about it a couple of times, and I heard that no one understands it. so I'll try to make it even much more simple here. So we need to be able to measure individual atoms, like what you see here. The atoms is inside the lattice, where it actually simulate the Hamiltonian or Fermi-Hubbard model. Yeah, some model, doesn't matter. And what we do is we realize a famous phase. Why it is famous? It's actually the phase that Professor Howden, who actually get Nobel Prize of Physics in 2016, about introduce the idea of topological phase of matter, and he used this phase to explain the topology of it. So it's a famous phase because it's the phase that make him get the Nobel Prize. That's why it's famous. Just remember that. And what we do to actually do the phase to trap atoms, we actually make a lattice from light. So if you put in the laser beams and make them interferes, it's in many directions that look like this. That's the point of laser. And then you make it interfere, it's gonna look like this. The atoms will be trapped at the very strong light here, here, and here. So it's gonna be trapped at the strong blob there. So that's how we create a structure of lattice, and we trap atoms to do that famous phase, whatever the phase is. And we again use a powerful lens to zoom into that small. So you see that individual lattice site have atoms, and those actually separate, individual lattice are separate by 1 micron, for example, in that order. So it's very small. The atoms are small, the separation are small. So that's why you need a very powerful lens and high resolution imaging system. So the camera that we use for take an image of atom is the EMCCD camera. So it is electron multiplier charge. Yeah, that's what he said. Yeah. So it actually the camera that they made for doing some looking on the star thing, take photons from the star, that actually I know. So they made for some place like NARIT, not us, but we actually, yeah, but actually we use those camera as well to detect atoms, because the atom actually emit very low rate of light. So we need something that is very powerful to see it. We do potential shaping using light again, make them in such a way that it's make the pattern of light look like this. And then the atom would occupy only the side that in the middle, in the dark place here. So you see the atoms actually align into a like a ladder system. We call it two-leg ladder. And yeah, that's how we do potential engineering. We use the DMD mirror, which is have an array of mirrors and can turn on and off light for individual spots. I think you use it in astronomy as well. Okay, and that's how we get it in the final. The potential look like this. and then individual atoms are trapped inside, and we can shape it into the shape look like this. And that's how we generate the Howden phase, the famous phase. Yeah. So not only seeing it, we want to see the spin of the atoms. As Ajahn Nung asked the question that how the magnetic field act on atoms, it actually make the atoms it actually have the famous effect called Zeeman effect. If you remember from your quantum mechanics 1 or 2.
Two, actually two. Thank you.
Thank you. Yeah, from your quantum mechanics 2, there is a famous Zeeman effect. So the energy will split depend on the strength of magnetic field. The thing is, we use the linear shift of the energy. We use only the linear part in such a way that the atom with the let me show you this first. The atom with the with spin up will seek the low field. So because of we put the gradient like this, it at the same time we load into the double wave configuration, the atom will seek the low field and go to the bottom, while the atom will spin down will seek the high field and go to the top wave. And that we can split atom from one plane into two planes. And then we move them further away from each other, because if them are too close, we cannot take an image without interfere between the other plane. So we take the upper image, we get these pictures. We move the focus of the imaging system. We take the bottom image and take this picture. And then we can construct the two pictures back to the initial one to see how actually they were in the beginning. And then you can see the individual atoms. If there are no atoms, you can see it as well. And then if there are two atoms in the same site, you can also see it, as well as the spin that we try to measure here. So it's a very powerful technique to see individual spin of atoms by using Zeeman effect. Yeah, from what I know until now, it's the only place in the world that can, we are the only lab in the world that can do this. So there is another way to measure spin as well. You kick one type of spin out of the trap, and then you can take a picture with only one type of spin left. So for example, you can try on resonant light, click all red dot away, and then only blue dot left. The thing is, that would work perfectly if you fill all the point here with red and blue only. But if you have whole or double, you're gonna be confused what they were. So that's the disadvantage of the technique of blowing away. But in our case, we see everything. We can see both density and spin at the same time. And that make us can construct a lot of feature of correlation that we interested. So I would not go into the detail how we construct it. It's too much, I think.
Hello?
So, yeah.
I go back to the lattice.
Here?
With, yes.
Yes.
So what is the double? What is the double here?
Okay, double is mean it's just the name of we call the quasi particle of two atoms in the same site. We call it double. So it actually because of this one is the which is both of them need to be different spin, because of what we do here is lithium 6, which is a fermion. it doesn't allow the same spin type to be in the same side because of it's gonna gain a lot of energy there. So only different type of spin could be in the same side. And that's what we call it doublon here. You can see there are two colors.
And the other question, how slow you have to separate?
This, you mean this stage that how long we need to do?
Yes.
Oh, that's a good question. You, since you do, of course, I forget to mention that what we do here is with degenerate gas. That means there are Brown state physics that we are interested here. Atoms are in the lowest energy. They don't want to be excited to the excited energy because of we gonna lose atoms away immediately. So what we do here, we need to do everything adiabatically in such a way that we don't excite atom to the excited state and lost them. When I say lost, because of its, we work with lithium-6, which is very light. If they are in the, if you think about the harmonic potential, atoms are in the bottom of the well, or on the lowest at n equal to 0. And if it excites to the upper one, it can tunneling very fast, and it would tunneling away from our system. And that's what not we don't want it to happen. So everything needs to be very slow. And the time scale that we do all of this, when I say slow, all of this has been done in couple of milliseconds. It's slow in our time scale. Compared to the lifetime of atom, which is about in a minute. Yeah. Okay. Yes. How can we experimentally probe the spin state in both planes? So maybe I didn't state it clearly. How do I hiding this? Okay. Okay, so both of them, each of them are different spin type. So you actually know that the upper plane is spin down, the bottom plane is spin up. So that's how you measure things, how you measure the spin. So you don't need to measure, yeah. So you know it, that the upper one is spin down and the upper one, the bottom one is spin up. From the Stern-Gerlach-like experiment here. Okay. Any more questions? So I could continue, right? So this work actually come from a big team. So I need to say thank you to the team from Max Planck Institute, as well as our genius theorists. So without them, we could not come up with a very nice idea to explain the system. Thank you very much. Okay. You can ask me more questions if you want. Thank you. Yeah, sure.
Turn on the microphone. So beside that, you can you did it at the first place in the world. What is a novel results or novel things that can explain about the work that can be published in such high impact journal like this?
So actually, topology thing is something that was actually well known, but it's could not be measured. It's well known in theory, but it could not be measured. In our experiment, we actually realize it experimentally. That's why it's like a breakthrough. Yeah. Is it hard to do it in solid state, Atanik?
So actually for probing the topological phase in solid state physics, it's slightly easier because we have like the platform where the electrons can actually travel, like there are direct electrons near the edge of the materials. So long as you fabricate the material in a pure enough form, usually using the e-beam epitaxy to grow the materials from the top and keep it in high purity. Then you would be able to probe them using quantum Hall effect and a bunch of other stuff. So yeah, it's based on the same theory, but the platform is completely different.
So the one that we do here is we try to simulate spin one chain. I'm not so sure. Can you do spin one chain in the solid state as well?
Spin one chain, I think that would be more correlated to what you call the Kitaev chain. Theoretically, if you could actually have like a strong spin orbit coupling materials in one dimension, and then you put it on a superconductor to have like the proximity effect to have like the topological superconductor having the topological phase of I can't remember if it's C2 or C1, but technically you can actually create like a spin chain in condensed matter physics as well. But I think it's a lot harder to manipulate, as even if you have the Kitaev chain, it's near impossible to probe like the single electron in the train. In comparison to your system, if you have like the trapped ions, which can represent like a quantum system by itself, then yeah, this is like way better way to actually like probe and verify the system. Like the theory has been predicted, but there had been zero smoking gun evidence. Even though there are papers published in Nature that say they have like smoking gun evidence of this topological phase, this Majorana fermions and stuff. Regardless, none of them could actually probe them one by one because the system is comprised of like the Avogadro number of the quantum state. So it's not like the trap ion approach. So yeah, so each approach would have its own benefit, something like that.
Thank you. So
Yeah, thank you.
actually, as Tanik said, that we actually use a powerful of single atom resolution and spin readable, such that we can actually prove that this is the real phase in the matter that we measure. Welcome.
So I have a quick question, if I may. So you have set up like the mod in Chiang Mai University. So what would be your next move after the mod has already been set up? What's the next project? Are you gonna try to set a couple more mods together and couple them together?
So we plan to load optical tweezer array into the system. So we're gonna trap individual atoms in individual optical tweezers. So we would like to see that we can trap in single atom array actually.
Sweet. So optical lattice is your next step.
It's different from optical lattice because of optical lattice would be we use light to interfere, such that we use interference to trap atoms. But in this case, we just use a beam focus down and trap atom in the foci.
Oh, I see. So basically, you would have a chain of interacting atoms, but they're not like in optical lattice.
Yeah,
that's very interesting. Yeah, looking forward to hearing more about your result. Thank you very much.
Thank you.
Can I have another question? This
Yes,
is just
please.
my curiosity. I heard that your lab is called QSIM, which is quantum simulation.
Exactly.
So, but I saw what you did is experiment. How can you relate the name of the lab to what you did?
So we our ultimate goal is to use atom to simulate quantum system. Like we want to generate some Hamiltonian that we can simulate like magnetic quantum magnetism, something like that. Yeah. So like study material stuff with atoms. Yeah.
May I have one question?
Sure, please.
What's your decision to submit the recent work in the Nature?
It's very hard question. to submit individual paper that we have done depend on how breakthrough we think the work are. So we have some that submit into PRL as well. Many in science and nature. So about science and nature is even harder to design. PRL is easy, like you do something and you think it's not good enough, let's go to PRL. But nature and science is something like we have last paper we go to science, this time let's go to nature. Yeah. Usually we do that. That's very. I would say that's what's really good time to be there. It's like you have a chance to do that frontier physics such that you always publish in those nice paper. Yeah, it's just like a matter of I think they just a matter of how instrument is ready for do those thing or not. Yeah, I think Thai people also are smart as them, but we just don't have enough funding to do so. Yeah.
Thank you very much for your comment. So from your point of view, oh sorry, was someone speaking in the?
Yeah, Ajahn Gop was speaking.
Oh, sorry, please go ahead, Kick up.
Yeah, you only want the Asian look. Yeah, how
Yeah.
you feel when you work in this environment?
I don't feel any different actually. They treat me very nice as they treat everyone. They are kind enough such that even all of them are German, they still speak English in front of me. So that's I think that's the respect that they give to me. So I think they are very nice. Yeah. So I don't feel any different when I was there. Yeah. So Ajahn Nick, do you have?
Yes. Just a quick question. Like, so based on your lab theme about the QSIM, so basically, your point of view of the theme between you, Ajahn Nithivadi, Ajahn Narupon, basically, when you have a quantum system, would it be best to create a simulation out of a physical system? So when under the theme of QSIM, what do you plan to do to once you have like all these trapped ions performing quantum like
to fix it, we do neutral atoms, and what we're gonna do is we use expertise of everyone that are in the team. Me, who actually expertise on single atoms or microscopic study, and Dr. Nithivadi, who actually are expert on Hamiltonian engineering using Rydberg atoms. So we're gonna do Rydberg atoms based on single atoms. So and Dr. Narupon, who actually have a very deep knowledge about quantum world. So we work together nicely. Oh, what did you ask? What we can do? I thought okay. So we actually plan to do in the first point, we're gonna try to do Ising model from the atoms. And then we will go to some model that is more complicated, like Heisenberg.
Okay, perfect. Yeah, thank you very much. Maybe I need to start teaching Ising models, like my professor Ajahn Yungyut to like the students in the undergrads. Yeah. It's amazing to see like things like this becoming more relevant and touchable in Thailand. Yeah, very exciting. Thank you.
Thank you. Actually, just want to mention when I was a bachelor student, I did Ising model with Ajahn Yungyut as well. So now I'm going to do Ising model again with atoms.
High five.
Yeah.
I'm glad to hear that.
Okay.
Sorry, I am not really in the quantum optics field, so my question would be more in the experimental part. I just wonder how powerful must the laser be to enable cooling? Or is it like, is there a lower limit for the laser power that you should use for this experiment? Or, but when you mentioned about the laser cooling earlier, I was just wondering how powerful must the laser be?
Okay. So it actually we use laser for everything. For the cooling, we need laser like in a watt scale to do the cooling. Of course, we lost between try to to control frequency and so on. But in the beginning, we need something like a watt, like that, at least 2 laser. And then we do the trapping with laser again. This, when we did with this experiment, we need 50 watt. 7 of them, 7 of 50 watt, and 100 one of them. So we have a lot of lasers. So it's very powerful one. It's the one that most powerful that we can buy in the world. So it's where we use a lot of power. That's the answer.
Then this brings me to the question that can you estimate the cost of the whole experimental setup? Then
Wow.
we get the idea how much we have to invest.
So depend on, so so the one that we plan to do in Thailand is, I have calculated the cost. It would cost about 70 million. 70 million, yes. I'm not so sure how long it's gonna take me to takes us to collect all the instrument, but for 70 million, yes. But the one that I have worked with in Max Planck, that would cost 3 times more, I would guess, 3 or 4 times more.
Can I ask some questions? So you say that at the MPI, you have like 2 PI and 4 postdocs, something like that?
Two postdoc,
Two
2
postdoc, 2
PI,
PI.
and 4 PhD students
4
in the
PhD
team,
student.
in one team.
So, is it possible if the postdoc want to create some experiment by themselves?
It's actually I don't know why, I don't know the right word to say. Is it called hierarchy? Yeah. So it's have a ranking, let's say that. So it's actually a really ranking over there, like master student will work under PhD, PhD work under postdoc, postdoc work under PI, and then there is 2 PI just because of we have PI and group leader PI. So yeah, the one who actually gained a lot of money. Yeah. Yes. So actually my supervisor or the group leader have experiment like this. Almost, I think he has 10 now. 10 experiment, like 10 small group. So 10 teams like this. Yes, exactly. 10 teams like this. So our group is like, when I was there, it's maybe 60 people in the big group. I think it's more now. But yeah. So yeah, it's a huge team. And fortunately, my the experiment that I joined is the one of his favorite one. Yeah. So it's the leading one. Yeah. So I can't remember his real name and her real name. Krishna and Jindamani. So he and she also joined the Max Planck Institute as well. One of them, Krishna, he is in the same group as mine. So hopefully he gonna get some interesting results soon. Okay.
I'm just wondering because you are using a DMD, and I know that you've been in the previous seminar in Narit where we were using DM, the deformable mirror.
yeah.
And I was just wondering that in your setup, could you use a deformable mirror instead, or it will require a
Hmm.
different kind of setup?
I think we can use it as well. The thing, yeah, yes. There are many devices that we can use for generate potential energy, but depend on speed and resolution. We pick up DMD because it's fast. It have a very high speed compared to the others.
Sorry, when we say speed, what exactly?
I think it's in kilohertz.
More
yeah.
than 1 kilohertz would you?
Yeah, more than 1 kilohertz.
Okay.
It's in kilohertz regime. I can't remember the number. Yeah.
Not even reach 1 kilohertz. That's what we want.
So any more questions from the student or from the Zoom? Maybe not.
No problem. It's my pleasure to be here and give talk to everyone. I hope that it would be useful with some of you. Thank you very much.
Please give a big thank to Ajahn Pimonpan.
Thank you.
But actually, I have one comment to the student, especially for PhD student, because some of you may think that, oh, I would like to go abroad during PhD, but you cannot with any reason you have. But for me, also from the experience of Ajahn Pimonpan, sorry, I think if you have chance to be there as postdoc, you will have another experience that is very different from to be PhD student abroad as well. Like she already said that you have more responsibility and you have that you will be really belong to their group and they just use you like their worker because you get money from them. So then you will learn a lot from that. So don't give up. If you cannot go abroad for PhD, you still have chance for postdoc in the future.
I would like to actually mention something, maybe for the last thing that I'm going to say. So you might think that working is just what you want to do when you are would like to do, but actually one of the successful key that I have is I work really hard. Doesn't matter he or she who are my boss tell me to do it or not. I work really hard, and it actually turned out that I make them feel very satisfied with my work, and they know that I actually do it my best every time I do anything. So I believe that I get into the group of blocks group in MPQ just because of my supervisor in at Optical University write me a very good recommend letter. So doesn't matter that what you are doing now is what, but just work hard. It's gonna return to you. Thank you.